So far we have seen the groups SU2 and the generalities about groups, and we saw their algebras for SU2 and SO3. So far we saw classical matrix groups, and we saw SU2, SO3 and SL2C as being equivalent to SO31 as being equivalent to SU2A cross SU2B, and this with a bit of inverted commas because there is a complexification involved which works at the level of algebra but not at the level of the global group. Now what we are going to do next is to and we saw that representations of irreps of SU2 and therefore SO3, which at algebra level are isomorphic. So we studied these and they are part of standard quantum mechanics. You get the raising and lowering operators. So now what we will do is do SU3 as an example of one higher level, but also as an illustration of how the general procedure works. So this group is important to elementary particles, but is also illustrates going to larger groups. So let me give you first a physical motivation why these are important groups. And this is really one of the greatest discoveries of the past century, which is so-called isotopic spin. This was an observation of Heisenberg that it does not matter to nuclear forces whether there is a proton involved or neutron. So you know that the history of this nuclear physics was a bit strange because the neutrino, which we might think to be a very unusual particle, was discovered first, and neutron, the big thing, was not known until 1931. But once neutron and proton were, and that resolved a lot of puzzles because the whole idea of why in the atomic weights two identical chemical elements had slightly different weights was not very clear, but that extra neutron, so isotopic spin clarified a lot of things. But at this point Heisenberg realized that the strong nuclear forces which bind the nuclei are such that electromagnetism is almost irrelevant there, and even protons which should be just flying apart. If you try to pack 30 protons into a nucleus, they have a huge Coulomb repulsion, but they are not flying away. So what it meant was that the nuclear force was much stronger and electromagnetism was irrelevant to it. So aside from electromagnetism, then there were still two species, neutron and proton, and the nuclear force treated them to be the same. So you try to think of from the point of view of strong force, proton and neutron are on same footing. But they differ in charge. In electric charge is irrelevant, seems to be subdominant. Okay. But there would still be two independent kinds of particles, because their spin is of course half, but their magnetic moment, other properties would differ. So Heisenberg proposed that actually they are like two projections, two spin projections of the same particle. So we have up electron. So we remember that we had said earlier that the analogy is to spin, because we had spin up and spin down states, and they can be flipped into each other by magnetic field, but otherwise they would be just on their own. So these mix by some interactions, but otherwise they are the same. So similarly here propose that proton state is equivalent to some kind of spin up and neutron is spin down with respect to something called isotopic spin. Which is an abstract concept. So concepts are of course abstract, but which is an abstract quantum number not associated with quantum number not associated with space-time symmetries. So thus was born the SU2 of isotopic spin, propose that nuclear Hamiltonian is invariant under SU2 of isotopic spin. So prescription is to construct the Hamiltonian entirely out of psi equal to wave function of proton, wave function of neutron, put as a doublet, as an SU2 two-dimensional vector, and its SU2 invariants. Like psi dagger psi, right? So that would be SU2 invariant, or things like psi dagger gradient psi, etc. Okay. So all these which leave rotation of proton into neutron Hamiltonian remains unchanged. So all those kind of terms can be added to the Hamiltonian, but not proton and neutron wave functions individually. So this was a big change. Of course, that there is a small mass difference between the two. Then you can by hand add some quote symmetry breaking terms that break the SU2 symmetry, but they would be small corrections to the main Hamiltonian, which would be isotopically invariant. Now, later on, there were some historical accidents. I shouldn't say historical accidents, but a sequence of discoveries which when they were first discovered, were not, their full significance was not realized. In elementary particles, which were essentially began to be discovered in 1950s and 60s after accelerators. It was found that there was proton, neutron and lambda. So, there were 3 particles. It's a slightly long story, but to cut long story short, it was found that 3 kinds of quarks, up, down and strange, made up all the low energy, by now we call it low energy, in those days it was high energy, hadrons and mesons. So, these 3 quark states, up, down and strange, were enough to explain all the particles like proton, neutron, lambda, capital lambda that is, and then things called psi of different kinds, psi 0, psi plus minus, and then of course pi mesons, pi plus minus, pi 0 and K0, K0 bar. So, there was a long list of such particles, but they could all be found as if they were a spectrum, excited spectrum of just 3 quarks, up, down and strange. So, that was a big discovery, and so a flavor SU3, we now call it flavor, in which psi was supposed to be up, down and strange in the order of increasing weight, but the electric charges are slightly different, that is a different story. But so, this is how you set it up, and then you have to write all your Hamiltonian out of these, okay, that was the understanding. Now, this is a really big break, because until now you had things like chemistry in which you had excited states, but you could visualize it as some electron cloud and coming together of 2 atoms to form a larger body, or more excited state of a particular atom and so on. Here you are actually saying that 2 different particles really were quote rotatable into each other. The identity of a particle was not unique, that it was negotiable under some internal symmetry transformations which were abstract. So, this was the beginning of understanding of the use of unitary groups in quantum mechanics and in elementary particles. At the point when these things were realized, SU3 was not part of physics at all. SU2 and SO3, the rotation group, had been all worked out in great detail, Clebsch-Gordon coefficients, this, that, but nobody knew about SU3. So, Gell-Mann worked, and what were the representations of SU3? So, the question is now of representations. For SU2, we had the raising and lowering operators J3, this algebra is enough to shows clearly irreps of dimension to j plus 1, right, and j equal to integer or half integer. So, if we have a 3 by 3 matrix, we may assume that a triplet like this is a representation, but what about higher dimensional representations? So, this was not clear at that point, and it had to be essentially worked out by hand, and we will go through a particular version of this. So, for SU3, first we need to guess the generators. And what we are writing down is what is Gelman's notation. And the idea is like this: if there is SU2, then if there is SU3, then it clearly has a subgroup SU2. Okay. So, suppose we start with a matrix lambda 1, which is 3 by 3. But such that its upper corner is essentially tau 1, Pauli matrix, and I fill the remaining with zeros. Then similarly we put lambda 2 as being 0 minus I 0, and then 0 0 0 0 0. So, this should certainly be in the list of, and we put a lambda 3 matrix, which is 1 minus 1, 0 0 0 0 0 0 and 0. Now, there should be similar matrices in which these things migrate to other locations. If you go to higher dimension, so lambda 4, and this is I should probably write down here from here, good. So, lambda 4 is where we make this one migrate to this corner. Lambda 5 is and you can guess that lambda 6 and lambda 7 are found in proposed in similar way. Where the ones then migrate to the lower box. But now you know that from counting that SU3 has to have 8 generators. So, we need an 8th generator, but we have exhausted all the sigma matrix structures. The sigma 1, sigma 2 structure has been all exhausted. We should also remember that you have to have Hermitian and traceless matrices to get the unitary determinant equal to 1, because if the trace is non-zero, then the determinant will come out bigger than 1. So, you need to propose something that is Hermitian, traceless, and would be diagonal. It will commute with all the others. So, the only way to make this is to write 1 1, and it has to be linearly independent from that. So, the only traceless matrix you can write, which is also not interfering with your SU2 subgroup. The top line is the SU2 subgroup, and the new diagonal matrix you are proposing should not disturb it. So it should be diagonal in the upper the upper corner. That only leaves you to put something non-trivial in the bottom, which you put to make the trace equal to 0. And then you need to normalize this. So if you normalize this by trace of lambda I lambda j equal to 2 times delta ij times the identity matrix. So this is because you remember Pauli matrix is if you square the Pauli matrix you get 1 identity, and if you trace it therefore you will get 2 as the answer. Gell-Mann made the choice 2, which I don't think is universal. The correct thing should have been to put n for size n, but it does not matter, that is the choice made and used by particle physicists everywhere. So all of these of course have this property, their square is essentially, the trace is 2. To make the trace of this equal to 2, you need to divide by a 1 over square root 3, because it will be a 6, 4 plus 2 plus 2, 6, the square, and remove a 2, that leaves 3. So you normalize by a 1 over square root 3. So this was the choice made, and then all you have to do is work out the algebra. Okay. We are not going to be interested in the details of the algebra, but let me just write down what it looks like. So the algebra is algebra of commutation. Algebra can be worked out simply by working through all the products, and one writes it in the form lambda a by 2 comma lambda b by 2 equal to I f a b c times lambda c by 2. And of course that lambda 3 and lambda 8 commute. I will not, so these f, a, b, c I think are, I will not spend time writing them here, but these can be worked out. Okay. What we want to now see is how we repeat the raising and lowering operator business. So here we see that there are going to be two kinds of raising and lowering operators, or rather 3 kinds. In the case of SU2, we had simply taken lambda 1, lambda 2, combined them into a lambda plus and lambda minus. But here we also have this pair and we have this pair. So there are actually 3 directions in which you can raise and lower, and this is done like this. So you define T plus minus to be equal to lambda 1 by 2 plus minus I times lambda 2 by 2. So these are our usual old isospin. So that is the isospin subgroup of the, there is a very cute accident that this flavor SU2, flavor SU3, its SU2 subgroup actually works as the isospin group, although the flavor we applied to these fundamental particles quarks U, D and S, and isotopic spin is proposed for proton and neutron. But it turns out that the way proton and neutron are composed of quarks, the isotopic spin just applies their without too much change. Also works as, physically applicable. As isospin, because proton and neutron only contain these. So, proton is UUD and neutron is UDD. So, they differ only in this middle entry UD. So, because this U and D are same, essentially the UD algebra works for proton and neutron, which is actually subgroup of this. So, that is a nice accident. That is how eventually it was discovered. So, I shouldn't call it accident, but that is how it works. But so coming back here, that for this T plus minus are the isospin raising and lowering operators of previous discussion, and then from 6 and 7 we call it U. And finally V equal to lambda 4 and lambda 5. And we introduce Y equal to 1 over square root 3 times lambda 8. Okay. If you do this, then you can prove the commutation relations which look like this now. T3 and of course, so T3 is same as half of lambda 3. So, T3 comma T plus minus is equal to plus minus T plus minus. Then Y T plus minus equal to 0. This is expected because Y was that 8th generator which does not interfere with the SU2. Then T3 U plus minus is equal to minus or plus a half U plus minus, and YU plus minus is plus minus U plus minus, and finally T3 T3 V plus. So, what we have written is the diagonal generator T3, diagonal generator Y, and its commutations with the raising and lowering operators T, U and V. So, what does this mean? We have now all these extra generators and things are being raised and lowered in different directions. So, the solution is of course to draw a two-dimensional diagram. We draw something like this, the T3 and Y directions. So, let me first draw here T3, which is the eigenvalue of T3, and remember that this these eigenvalues, because they are SU2 eigenvalues, they are half integer, integer and so on. So plus minus half, plus minus, so put a 0 here, 0 was also of course allowed, and plus minus half, then plus minus 1. So these are the possible things for T3. But now, and you could raise and lower using T plus T minus. Okay, so T plus takes you here and T minus takes you here, raises the eigenvalue by a unit. Okay, so this is minus 1, this is 1, and these are half. So the action of T plus and T minus changes the eigenvalue of T3 by 1 unit. This we knew for SU2. But now we get eigenvalues of Y as well. And the Y eigenvalues are also raised and lowered by U plus and U minus by 1 and minus 1. So let us put a 1 here and a minus 1 here on somewhat similar scale. But the action of U is also such that it reduces the value of T3 by a half unit, and action of V is to increase the value of T3 by half unit. So what happens is that we have new eigenvalues here such that the action of V takes us to this, right. V, because we want to increase both. Okay, here the sign is minus. Yeah, so this should be U. So this is U, whereas this point is reached by action of a V. Similarly, we can see that we will get these points minus half and minus 1 by action of U minus, because if I have U minus, then it reduces the value of Y, and it also reduces it increases the value of T. Sorry, what did we get? So Y value is increased by U and T value is reduced by U. So these two are, wait a minute. Yes, so that's right. So both of these, which increase the value of Y by half, are plus are in this and minus are in the lower quadrants. Okay. And here this lowering is done correctly by V, and the lowering, this is, the reduction is done by U. So this is U minus, this is what I have drawn at least, U minus and V minus. Is this correct? Okay. So what one does is to actually introduce first the simpler representations, which are just triplet. This just shows the direction of increase and decrease, and it's anyway got slightly messed up. So we start with 3 and 3 star, which are drawn as So these two are separated by, this is half and plus and minus half, and this is plus 1. Again, of course, these are T3 and Y eigenvalues. And we call this the 3 or 1 0, and this 3 star or 0 1 representation of the two generators Y and T3. So these are the triplets, the UDS that we wrote. We are now going to represent it like this, and since U and D were forming an SU2 doublet, that is what are these two. This is essentially U. I don't want to clutter up the diagram, but anyway, just to indicate. U and D are here, separated by T3 value of 1, and then we got the new state here S, and then these are the starred ones. So the old SU2 isospin will continue to be there on the horizontal axis, and then plus we get the extra thing. Now the trick is that we can make higher dimensional representations. I will not try to give you the graphic methods because I actually want to do algebraic one, which is more reliable. But to quickly show the historically what was important was that it was possible to now find tensor representations of these, so products of these. So just as if you have a vector Vi, you can make a Vi Vj, a higher dimensional, higher rank tensor out of it. You can make higher rank tensors out of 3 times 3, 3 times 3 star and so on. So 3 times 3 star contains a representation which is 8. So it splits into an irrep 8 and a 9th which is SU3 singlet. 3 cross 3 produces 9 states, and as physical applications I am actually saving space, which is cramping the thing a bit, but it's okay. So as it worked out, the pi mesons fell on an SU3 diagram of, so of course Gell-Mann had to identify what physically Y meant, and that Y generator was hypercharged. Equal to T3 plus, equal to B plus S. So electric charge is, that's right. So this hypercharge is baryon number plus strangeness, and factor half has to do with normalization, but I think it is, or no, there is no half kept here. And Q, electric charge, would turn out to be equal to T3 plus a half Y. Yeah, half goes there. So with making suitable charge assignments, one finds that this is pi minus, pi 0 and pi plus. They form a isospin SU2 triplet, just like a angular momentum L equal to 1 state, minus 1, 0, plus 1. But then there were other mesons which fit here, and these are called K0 and K0, K plus, K minus and K0 bar. So although K0 was a neutral meson, the K0 bar was not same as K. So in fact it is, one contains strange quark, one contains S bar quark. So they are opposite so US bar and U bar S, something like this, whereas the K plus K minus are charge mesons. So these 8 fit here, and you of course have a 9th particle if you square take 3 times 3. That one is usually indicated nearby, and that is called an eta meson. Okay. And this eta meson, frankly till date, which particular particle state in those excited states that so K and K0 bar are reasonably long lived mesons. So they fly through your detector and you can see them splitting later, and it's easy to identify all. And mesons of the pi mesons of course leave long tracks in the emulsions. But all other particles that were discovered were all much short lived. So they are only seen as resonances, and the width of the resonance basically tells you the mass of the particle. The time scale for which it lives is inverse of the mass of the particle. And so this is a physical application. There was another, well, so I meant to draw the other diagram. Let me draw it anyway, because that historically that was the most important thing discovered. Gell-Mann went on to propose that there is a representation 10 dimensional irreducible representation, which now looks like this: T3 Y, on which here we have these 4 states. The jump is by 1, so these are half integer representation of T3. Then there is integer 1 0 minus 1, and then another plus minus half. Now these particles had been discovered, okay, and these were called N star, and there are various charge states which I forgot to write: sigma star and psi, so-called psi hyperons. So they fall on this. If we think a little bit, we can, and this is y, and if we apply this formula T3 plus half y, we can work out the charges. So for example, this has to be minus 1 0 1, and this may start with 2 1 0 minus 1, something like this. But so these are all separated by shifts in T3, which would change q by the same amount. So they differ in charge by 1 unit. The interesting point was that these were known, and Gell-Mann, using this formula, laid them out like this, and then he realized that that did not complete a representation of SU3. So you needed something here to make up the full representation, and so he proposed that there should be a particle here, and this has actually omega minus. So it is omega of charge minus 1. That is what fitted with rest of the multiplet. So this decuplet was more or less by matching. So it was like spectroscopy of the hadrons, and from which, with some educated guesswork, he guessed that there was this representation 10, which we can work out next, and that this particle should exist. Not only that, this splitting along the direction y of this multiplet is proportionate. So if you know this distance, the mass difference between, so this row was all roughly same mass. Each row has approximately same mass. So knowing the mass difference, mass grows as you go down. These are simply observations, okay. By putting things on it, and you see that this is how they fall. In fact, you would put them in same row because they all have same approximately same masses, and their isospin differences can be found because the decay modes would contain pi plus or pi minus. So that gives the I3 difference to be correctly plus or minus 1. And so finally this had to exist, and so omega minus can be predicted along with its mass. So this was one of the striking discoveries of 1960s. Okay. But that launched this whole idea of an internal symmetry of particles, which is not just something spectroscopic, which is not just some excited state of something, but fundamentally distinct species actually have an internal symmetry that connects them. So this is one of the biggest discoveries of the past century.